What in the world is this equation trying to say? I mean, it has ordinary derivatives, partial derivatives, integral over both area and volume. It is as if most of differential and integral calculus is in one equation. On the other hand, if you look how powerful this theorem is in context of fluid mechanics, it has its own right to be that way. I mean, literally, here is what I mean by powerful. Using this equation, which by the way is famously known as Reynolds transport theorem, you can derive almost any equation from fluid mechanics. For example, you can derive this complex set of three equations known as Navier-Stokes equations, or this one also known as continuity equation. How about this simple looking equation? Or maybe this one. You name the equation from fluid mechanics and using this theorem, you can derive it. That's how important and powerful this equation is. Must be complicated even to comprehend such equation, right? Well, this is what this video is about, and my goal in this video is to make you appreciate how such vague and complex looking equation can seemingly become senseful, not just mathematically but by using physical and abstract insights. Later in the video, we will soon see how interpreting our complex looking equation is very much similar as interpreting this simple looking equation. But first, we need to wrap our head around some general and important yet subtle concepts from fluid mechanics which are important in order to understand our equation. Going in depth of such concept is of most importance, especially if you are studying fluid mechanics, but this is not what this video is about, and we will just barely touch these concepts as they are foundation of any core concepts in fluid sciences. We will first start with the distinction between how equations for solids in solid mechanics differ from equations for fluids in fluid mechanics, which brings us to the topic of Eulerian frame versus Lagrangian frame. Say you are dealing with a particle, you have initial position vector attached to it, and as particle moves, you calculate the rate of change of position vector attached to that particle and use governing equation like force is equal to mass times acceleration. Even if it is a solid made of number of particles, every particle assuming that they are one as solid move with same velocity or acceleration, and thus we can apply governing equation just to the center of mass of solid. As if that single point is enough to represent the changes that happen over entire system, and you escape with dealing with just a single equation. That is Lagrangian frame for you. However, with fluids, since fluid continuously deform, you have to track each fluid particle and forces acting on them at each position and timestamp. In practice, using Lagrangian frame even for few particles is next to impossible. What's more, fluids are dealt on continuum basis, and if you have a complex fluid flow to evaluate, it has many intricate dependencies among each properties of fluid. Even computers are pale in front of doing such tasks, let alone we do it by analytical way. To overcome this and make fluid analysis analytically, we make use of Eulerian frame. To present vaguely, the basic idea is using vector field at each position and time. Earlier in the video, the vector field that was plotted was a velocity vector field. At each point in space, you compute the scalar values according to the function. In our case, say we take point 0, 3 and substitute these position values into our function. A quick side note, the position values are taken as radians by our sine and cosine terms in the function, which outputs the following numbers that are used to scale the unit basis vectors, which are in turn added to get the resultant vector, and as a result, each such vector is plotted at the respective evaluated point in flow space. And there you have our flow field. Now the inner fluid particle in the flow domain follows the velocity field at each point in space over time, as if the particle is guided by each vector at each point in space. Thus, by doing so, instead of having track of change of position vector over time for each individual particle, we have a single vector field equation that governs the flow at every position and also over time if the flow is unsteady. There are more subtle details and philosophical points about how framework of Eulerian frame works, but the base idea is the same and remains as a topic for entire new video. Moving on to the last small concept which we need in order to understand our theorem is system definition versus control volume definition. Again, the basic point comes down to Eulerian frame versus Lagrangian frame. However, I would like to point out some concepts separately here. Consider this circle to be boundary of our system and bunch of these dots as particles with some mass that are there within our system. A system thus is defined to be of fixed mass, thus no mass enters and leaves the system. However, extensive properties, that is those who depend on mass, like momentum, can change within the system itself. Thus, in order to accommodate those changes and to keep the mass constant within the system, you see the system boundary itself going change, which again happens to be too tedious to work with in context of fluid mechanics. And thus the concept of control volume, in which we fix our region in space, or which we monitor the change in fluid properties, so the mass can enter and leave the control volume, and along with it, it brings the change in the properties of fluid within the control volume. And that is exactly what we need to evaluate fluid flows. So this is an important concept to have, since this is what our Reynolds transport theorem is based upon. This brings us back to the equation that we saw earlier, which serves as a link to understand our equation in much more simpler terms. The equation says as following: E dot Cv, E is energy here, which implies rate of change of energy over time within the control volume, is equal to the energy E that comes into the control volume minus the energy E that goes out of the control volume plus some energy E that is generated within our control volume. The whole purpose here is to model how amount of energy changes as energy can surge in and out of our control volume. Let us try to understand why this equation has a certain form like that using a much familiar attempt of taking similar example, which in my view is more fun and relates to our energy equation in even better and logical way to make us easy to understand it. Consider a simple case of how balance of money in a savings account changes and how you would calculate what balance you are left with after having certain interactions with the bank. What do I mean by interactions? Well, consider on a certain day you deposit certain amount in your account, maybe 10 rupees. And after a whole month, you went and withdraw say 5 rupees out of your account. So how much balance you are left with in your account? It is as simple as subtracting the withdrawn amount from the deposited amount, which leaves us with the 5 rupees at the moment in our account. Pretty straightforward. And also it looks very similar to the two terms that we have here, right? So I guess now you can reason why our energy equation has these two terms. So as to calculate the energy remaining in our control volume after a certain amount of energy enters and leaves is simply calculable by subtracting energy that went from the energy that came in. So I hope at least these two terms make sense. Okay, what about this term then? Well, for the amount of time period you keep money in your account, the bank also offers you interest over that amount. Say this bank offers interest of 10% per month. So for 10 rupees, at the end of the month, we have extra 1 rupees in our account. So we need to add that in our balance equation to get the correct amount of balance that we should be left with in our account, which gives us of about 6 rupees. So very similar to how banks generate money for you for keeping it in account, which you need to add to in your balance equation, you need to add the energy that is generated, which might be due to some external or internal source, to the energy balance equation to have the correct amount of energy content within the control volume. And that's how this example takes care of this third term. So isn't this calculation of our analogous balance in bank scenario a very familiar and logical example to understand why our energy equation has the given form? I want you to hold on to this case and how it relates to our energy equation in mind, because at the end these two concepts are exactly what our theorem is inheriting and displaying in much more mathematically complicated way. So until now we have engulfed the surrounding concepts involved with enriching the conceptual vocabulary for just reading our theorem. And now it's time to move on to the next main part where we try to visually understand what our theorem is trying to tell us. Our goal for next few minutes is to write equation that governs the rate of change of some fluid property, which we generally term as n within some region, which is our control volume. Just as we tried to model amount of change in energy E that our region experiences with the conservation of energy equation, here we are trying to conserve any fluid property, which could be linear momentum, angular momentum, or even maybe mass itself. If this term says written for n equals to mv, then it would result in straightforward force acting on our region, which we know is written for system definition whose mass remains constant. But since we are dealing with the fluids which are dealt using control volume, across which mass may enter or leave, that net moment of mass will also contribute to the force acting on our control volume. Thus, there is need to derive new set of equations that will account for this contribution to our control volume. And for the matter of fact, that is one of the motives behind Reynolds transport theorem, which is to derive equations for control volume rather than system and form a connection between them somehow. You will see what I mean by that in a short time. For the purpose of this video, we are going to take n as mass. That is, we would like to write dm over dt for our control volume, which if was written for a system would have been 0. And I want you to treat mass for the sake of this video as particles, each one with fixed unit mass. So for 9 particles inside our region, say each has 1 kg of mass, then there is total of 9 kg of mass within our control volume. Okay, so on to the next part. For that, let's bring our old velocity vector field where we base our control volume, which for simplicity is retained as circular. Now the way we approach writing rate of change of property for our control volume is we let a system that at time equals to 0 is at some location, and as time passes it moves along the path governed by our flow field, and at time t it happens to be coinciding with our control volume. Now we let some additional time delta t to pass, and so our system gets a little nudge along our flow field. Thus at time t plus delta t, we have our system, and at time t, we have our fixated control volume, due to which we recognize three distinct regions and number them as 1, 2 and 3, such that the region 2 is a special region which is a part of system at time t plus delta t and also of control volume at time t. Then we have our region 1 which is solely belonging to our control volume at time t, and region 3 which is solely belonging to our system at time t plus delta t. So we have identified a special region 2 as part of both system and control volume at two different time instants. Honestly, if you ask me, this gets confusing at times because there is a region which exists at both time and is a part of both system and control volume. But really, what we should think of it as some region that is there in our flow field which is there at all times only to be the part of our control volume at time t and also to be the part of our system at time t plus delta t. And whatever changes takes place in the region reflects to the change that is happening within both system as well as control volume. Now since we have made use of system definition as well, we take a clever approach in deriving our change equation of some property over control volume by making use of system approach. For that, what we do is we write the sum of property n over two regions at both times, meaning property n at time t can be divided as property n which is there in region 1 at t plus the property n which is in region 2 also at time t. Similarly, we can derive property n at time t plus delta t is equal to the property n which is in region 2 at time t plus delta t plus the property that is in region 3 at time t plus delta t. And you can already see that these two property equations belonging to two distinct time intervals are written for system definition, since adding count of dots in both cases is the same, which is equal to 9 dots, which also if you arrange this equation as definition of derivative over time, there is no change in count of dots, thus the value of dn over dt is equal to 0, which checks out with our system approach. Now we rearrange these terms, sort of clubbing terms belonging to same region at two different times, like this one here. Then these two terms are made to stand separate but have some similar vibes and appearance emanating from them. Take a moment to grasp how and why it makes sense to rearrange the term in this manner, since for one reason they also have a lot of subsets going on. The motive for rearrangement like this will be clear when you apply limit to each term and analyze them separately, as the equation you see here is going to slowly mold into Reynolds transport theorem which we saw earlier. And thus, now it's time to look onto each term bit by bit. Clearly you can see over time, our second region has witnessed change in mass from 5 kg to 4 kg. That is exactly what this term is asking for in finite difference state. Moving a step further, if you let limit delta t tends to 0, you actually approach interpreting this term in terms of definition of derivative. And this is where I leave the part of interpretation up to audience, since it comes down to how you have manifested the visualization of derivative. If you are someone who has watched the 3 Blue 1 Brown series on derivatives, you can relate to the fact that the nudge shown for system here is exaggeration for illustration purpose. And really you should think of it as a tiny nudge, almost making it indistinguishable. And then when you apply the limit and in the limit this term approaches to the definition of derivative, making it as a dn of 2 over dt. Well, technically it's a partial derivative as we are dealing with both time as well as spatial coordinates. However, besides just interpreting the limit delta t tends to 0 as a derivative, there is yet another reason to ponder over what this is implying, and this is where it really gets interesting, since you can also think of letting delta t tending to 0 as if you are reversing the time and making system coincide with the control volume, and thereby our second region, which was just a small region earlier, now tends to coincide more and more with control volume and engulfs the entire control volume in the limit as delta t tends to 0. Therefore, you can actually substitute dn of 2 over dt as dn of cv over dt, meaning now we can interpret this term, which was earlier rate of change of property in second region, to be in the limit same as rate of change of property within our entire control volume. That is something which comes geometrically straight after applying limits, don't you think so? That's it then. We have our first term in our hand. But wait a minute, if you look at our original equation, you will see it written as this. So what's the first here about? What's the relation between capital N and small n? This is where topic actually merges with fluid mechanics other than just being mathematical. The short story is, the small n you see here is actually capital N divided by total mass, which makes it an intensive property, which is also known as specific property sometimes, and it's something that doesn't depend on the mass of the system. Basically, you take the capital N, say mv, you divide it by total mass, you get just a v, which is momentum expressed per unit mass. So just v is an intensive property for momentum. Similarly, if capital N equals to m, which is total mass, then small n would be simply 1. For my view on the side note, this is done usually because in fluid sciences, it is easy to measure mass in terms of mass flow rate using mostly analytical, sometimes empirical, as well as practical techniques. So if we calculate a property per unit mass, in mostly analytically easy to deal cases, you just have to multiply that property per unit mass, small n, by the mass flow rate, which is in some sense easy to calculate. For example, when you have a velocity field defined in some region like ours is, we already know with what velocity our fluid is going to engage. That is, we already have V defined, we just now have to calculate the mass of the fluid that flows along our flow field, which for the most of the part is pretty easy to calculate using some analytical formulas like this one I showed earlier. And then you have to multiply the calculated mass flow with V to get the momentum of the fluid passing through our flow field. So on right hand side you can multiply with m, which in turn can be written as density times some volume element. That's nothing but by the definition of density. And there you have it. The integral is only there because fluids are dealt on continuum basis. So you have to divide your control volume into small discrete volume elements and then multiply that with the density, which in itself might be the function of independent variables making up our volume element. Same with our specific property small n, which you also need to multiply to get capital N. And then you integrate it by letting discrete volume element tend to 0 over our entire region of intended control volume. So moving on to the next two terms, which you will see that both of them are quite telling the similar story. And one important disclaimer about these two terms is that rather understanding both of them just mathematically, it's important that we also ask questions like what are these terms are geometrically as well as intuitively telling us. We will see what I mean by that in a while, but keep that in the mind. We will have our attention at the term involving third region first. The first thing to notice in this term is this, even if it has got looks like a being a derivative, it's not. Since for derivative over time, you would need the difference of property n in the numerator at two different instants. But this term has got property n only at time t plus delta t, which is in turn divided by delta t, and thus we can't interpret this term as some derivative or for that matter of fact, not even entirely mathematically, as we did with the first term of ours. But then the fact that we can't treat this term mathematically is just replaced by many possibilities of intuitive ways you can think of this term. Perhaps physics or geometry of the situation might have to do something with it, as this theorem is tied to fluid mechanics. And that would be right way to approach this, but we will see that in a moment. So one way, an obvious thing to first look at is by letting limit delta t tend to 0 and then ask some certain set of questions which will not just have mathematical attribute to it, but some abstract and geometrical sense as well. So first we ask, letting limit delta t tend to 0, what can we make out of this term geometrically? Well, the answer to that is visually clear that our third region is getting smaller and smaller, and in the limit it tends to coincide with the surface of our control volume. Just like the way it happened with the second region, with only one difference here, that unlike region 2, which in the limit merged entirely with our control volume, the third region here in the limit is not being entirely coincided with our control volume, but only with the part of the surface of our control volume, highlighted by the yellow region here. Here it is one more time. The blue appealing third region shrinks and shrinks, while eventually becoming part of the surface of our control volume indicated by yellow color. All this because we let limit delta t tend to 0. And that's how we take care of the limit. But we still haven't made any progress with what this term actually is. For that, we take one step further and ask yet another important question. What this term is implying intuitively, or moreover abstractly, when our blue region coincides with our yellow surface. Or rather, rephrasing the question precisely, what happens to the property n, our so-called particles, that are there in region 3 when we let that region coincide with the surface on the control volume in the process as limit delta t goes to 0. Well, at least now our way of interpreting this term has changed to asking the question that what our property n is doing at this yellow highlighted surface. And it's important we remember why we came to such conundrum at first place and what does it even mean to reach at this point where you try to interpret a much rather mathematically appealing term by asking some vaguely notionized question. Well, if you reflect back at it again, at a certain point when we first look at this term, there are not a lot of things going on with it, as it has only one term n up numerator which has more of a physics appeal to it, as in a sense it is a property of any fluid. And on the second, it's divided by delta t, which is our nudge in time. For that, we supported our reasoning by our geometric intuition of third region shrinking and shrinking as delta t goes to 0. But other than that, we could not have possibly made any progress in contemplating what this term is. So we took a rather subjective turn towards interpreting this term, as if it is telling us to transcend beyond objective world and to seek for what happens to our property n on the coincident surface when our third region coalesced with the same surface, and this all happens in the purview of limit. However, let's add a little bit of concreteness to our question, since we can't always rely on the realm of abstractness to get a concrete answer for us. To do exactly that, we just tweak our question a little bit by asking what is happening to the mass on the surface of our control volume, since we had a property n assumed to be the mass that we wanted our equation to represent. Well, its answer is almost trivial, as you see that the mass is leaving the control volume from this yellow control surface. Thus what we should be modeling out of this term is how much of total mass comes out of this control surface that is just the part of our control volume. More technically, if you approach, it's asking us to compute the amount of flux of mass out of this surface. And thus now it's clear that all we have to do is calculate mass flux out of this region, since that's what this term is expecting out of it. So how do we do that? Well, let's bring few particles at some time on the surface, and we will focus only on those particles that are about to leave our control surface at that moment and highlight them by green color. Momentarily, they are having following velocity. And this is not something out of the blue, rather those velocity vectors are nothing but part of our velocity vector field, and our fluid particles which happen to be at that specific point and time happen to take up that velocity. Also, people familiar with the concept of flux will concur that when it comes to computing the flux, you have to deal with outward normals to the surfaces. At this point, having intuitive knowledge about flux will do you good to understand the following better. But anyways, on the surface, we have outward normals like this. So we have that information in our hand. Now the way to calculate the flux is using the velocity components, since they are already defined. To do that, we project the velocity vectors onto the surface normals, meaning we take dot product of velocity vectors with the normals, denoted as eta here. And the quick thing to notice is this: dot product is going to be the positive term, since both velocity vectors and the outward normals are in the same direction. Then we multiply this term with small elemental area followed by the density and integrate over entire control surface. That is the yellow colored arc, since that is where our third region merged and not the entire circle. And at first, it might seem we have went nowhere, since we wanted to calculate flux of mass, but never we see the term mass, instead just velocity, density and area. At this point, getting into intuition of why it's done that way, we will be way off base. But the smart and quick way to see that what we have written here is indeed mass flux is to check the units. Velocity is meter per second and area is meter square. Thus when we multiply these together, we get meter cube per second. And also we have density, which is kilogram per meter cube, which when multiplied results kilogram per second. And that's just it. Clearly, unit tells us that this term is indeed mass flux. And what's more, it's per second, that is we seek for rate of mass flux, which makes sense since I have already mentioned with fluids, the rate at which changes occur is important, like whether mass leaves out with 5 kg per second or 4 kg per second or 10 kg per second, that matters. Well, for generality, we also have n over there, which in our case is simply 1. Since what we have considered to derive our equation is for n equals to m, so we are left with small n as 1. So for our case, it's safe to ignore that and we are left with this term. Again, the integral here is to account for continuum basis, since we can have density and velocity defined as a function of space, so you divide area element and compute those terms and integrate it to get the full sense of mass flux over our control surface. And finally, we are on our way to interpret our last term, but you might have already noticed our third and final term is no different than our second term up here that we just dealt with. And also, you will see its interpretation is very much similar to that of our previous term, with little bit of change such that the property in this term is representing that is there in region 1 instead of region 3. But still, it's fun to walk through, and also it's important to see how it differs from our previous term. Due to its similarity with previous term, it almost begs us to ask the same question again. What this term implies as the limit delta t tends to 0. Well, as we let delta t go to 0, we again see that our first region shrinks in the process such that in the limit it tends to coincide with yet again some part of our control surface of our control volume, which is again geometrically straightforward, and thus we move on to asking our subjective question, that is what happens to our property n, which is mass on that control surface. Well, again, if you derive analogy from our last term, it's not hard to discover that mass is entering our control volume via that yellow highlighted control surface, and thus modeling our third term is same as calculating mass flux that comes into our control volume. So for that we again take few particles to deal with this. We have our velocity vectors attached to those particles, and thus to calculate mass flux we project velocity vectors onto the normals to this surface, which as you notice are now in opposite direction to the velocity vectors than when it used to be on the other side of surface for our second term. So when we dot them on the surface normals, which is same as projecting our velocity vectors onto the line passing through these normals, we are left with the projected vectors that are highlighted in blue color here. Since the orientation of velocity vectors is opposite to the normals, this poses a question of what change this brings to our term. Well, simply, when we dot velocity vectors with normals to this surface, it will output a negative dot product, and we have to include this change of sign to our term. But then the rest of the term remains same, as all we had to model was mass flux through our control surface, and that is exactly what we also did for our last term, only there we had outgoing of mass flux, and here we have income of mass flux. Again, the only change that is reflected here in this term is the negative dot product, which in previous case was positive, as the velocity vectors and the surface normals were oriented in same direction. For rest of the term, again we multiply by density times small elemental area, and we also have our small n, which is 1 for our case, and thus we are safe to ignore it. After that, we can integrate it all over the control surface, and then we are left with our final term, which again noticeably is exactly same as this previous term here. Isn't that right? And just like that, we have made up meaningful interpretation out of every term that we have seen so far, and now it's sort of imperative for us to generalize our equation, since for sake of this video, we derived our equation taking mass as an example of property, and also to get an overview of what we have accomplished so far and what lies beyond just the technical comprehensive meaning of our equation. By which I mean we will be discovering other things that are hidden within our theorem, which are more subtle to notice and at first might seem bit trivial concepts to attend to. But anyway, they are essential philosophical concepts according to me, and also by doing so, it will also lead us to why our theorem picks up the given name, which is Reynolds transport theorem. Again, we remember the infant form of equation that is supposed to turn into Reynolds transport theorem that we saw earlier. With that form, we went on interpreting our three terms which constitute the right hand side of the equation, which using limit turned into our final form. Now what is left to interpret is the left hand side of the equation, and it's not so difficult to see what it means since it has property n at two instants Rn in the form of derivative, with noticeable thing that the property is not specified over any specific region. So for our case, which is n equals to mass, this term will simply go to 0 since at all times mass doesn't change for any system. This detail is important because it can be viewed as a result derived from a proposition using our system definition. As you remember, for system you can't have change in total mass as time passes. So speaking in general, for any property we can reserve this term as the one dictating change of property for any system definition, and thus when the limit is applied we can have it written as proper derivative of property n for any system. Really though, I mean seriously. Earlier you said that the equation that we were going to derive will represent the changes over control volume and not any system. So why the term on the left hand side is derived as change of some property n for any system? And even if we agree to do that, how it makes sense to equate these two terms as both are derived for different definitions? Well, this is the point where our theorem is most subtle to interpret, by which I mean if you carefully compare these two terms, you first notice the term on the right has an integration over the volume of our control volume and then divided by del of t. Thus clearly it's an indication that whatever this term is, it is for derivative of some property, just broken as term to be first integrated and then differentiated. So it's almost the same term as one in the left, but for some reason their appeal to us is different in terms of things that make up those two terms. But recalling few earlier things, we have capital N is equal to N into capital M, which can be written as rho into dV. So we can actually resubstitute N in place of N rho dV, and thus we are clearly able to see that these two terms are almost same. Only the one on left hand side of equation is for system definition and the other on the right hand side is for control volume definition. But don't be too hasty and quick to conclude that these are one and same thing, as we have equal to sign in between them. Well, as said earlier, because one is for system definition whose mass is constant and the other one is for control volume which can have variation in mass, as our focus is over fixed region in space, which clearly implies they can't be equal to each other. And also don't forget, we have this second term in our hand which is added to our first term here, so it's important to not to ignore the presence of our second term and what it has its part to play with these two terms. Once we have second term added to the first, then we can have equal to sign between the left hand side and the right hand side, which if you think profoundly is trying to say, hey, the rate of change of property n within the system is equal to the rate of change of property within our control volume only when you consider the net flux of property which flows in and out of our control volume, which is taken care by adding the second term over here. So in order to equate those two, you have to include the addition of this extra term over here highlighted in green. Otherwise, there is no point in equating these first two terms. They won't be equal to each other. Okay, so immediate following question would be why it is the way that we have to add the second term over here. After all, both first two terms are dn over dt, so they kind of mean the same, right? And what changed the presence of system and control volume as subscripts on two terms reflect in terms of their inequality? And the answer to this brings us back to the basic definition of system and control volume. In a sense, what I mean is that how dn of Cv over dt is different than dn of system over dt is hidden in the physics they describe using their respective definitions. Okay, but a minute, let me put in a more constructive way, and what else is the better way to explain other than using an example? So again, let's take n as mass that we want to conserve as property, which converts our equation to this. So for who know how many times we have gone over this, and since we have mass as property, we can easily take this to 0, right? After that, while dealing with this term on right hand side, as it is for control volume, we need to fix some region across which we say mass flux of 5 kg per second comes in and mass flux of 3 kg per second leaves out. So 2 kg of mass has accumulated within our control volume, which changes the mass within our control volume. So clearly over unit time we have dn of Cv over dt as 2 kg per second, right? Because before influx of mass we had 0 mass within our control volume. After 5 kg of mass came in and 3 kg of mass left, suddenly there is 5 minus 3 equals 2 kg of mass within our control volume, which means over time there is accumulation of 2 kg of mass, which can be thought of change of property within our control volume, which is measured by control volume definition. So now can you equate these two without consideration of this third term here? Clearly not, right? As this has dn of dt has a value of 0 and other has a value of 2 kg per second. So clearly you can't write equal to sign between these two. But now in comes this third term, which as we went through its interpretation in this video is just a fancy mathematical way of consideration of net flux through our control surface. So when we do it for this example, we had outflux of 3 kg per second, we subtract it from influx of 5 kg per second. Why subtract influx from outflux? Well, remember this flux computation is over surface, which involves dot product of velocity vector and surface normals. Thus we end up with positive sign for outflux and negative for influx. This gives us the result of minus 2 kg per second. And now with this added to 2 kg per second, it gives us 0. And thus we have now two terms on the both side of equation with the same value, and thus it now makes sense to equate these two terms. So again the keynote here is that we had change of property term for a system and similarly for control volume, but based on their behavior due to how they are defined, we can't simply have them to represent one and same thing. But when we add the following term to our control volume side of equation, suddenly this term serves as missing link, which when taken into consideration would go on equating how change in the property of system be equal to the change in property of our control volume. And this thing right here is why our theorem picks up the name of transport theorem. In a sense, using this equation, you can transport between system frame to control volume frame as they are made equal to each other by our Reynolds transport theorem. And just like that, it's the end to what this theorem means. But there are still tons of loose ends to tie which are way beyond this video scope and don't just only depend on how you interpret this equation, but rather have more to do with solving of fluid related problems that one might go through while taking fluid mechanics class. Nevertheless, I would like to cover even those untouched details in some further videos that I might come up with, which will have more fluid mechanical tone to it. But for now, I have to take my leave. See you soon.